Usually data is organized as arrays. The one-dimensional arrays, that is lists or columns, are called vectors, and some rectangular arrays are called matrices. Now let us consider operations which could be applied to them. An n vector is just a tuple of n numbers. They can be organized as a list or so on, but any tuple of n numbers is called an n vector. Maybe you know that vectors are arrows, or the vectors are, for example, in some programming languages, a vector can be an array of numbers of any kind. But now in linear algebra, n vectors are arrays of n objects. Later we'll consider also abstract vectors, but let us concentrate now on these ones. For example, one vector is just one number, so that the set of all one vectors is the set of real numbers. The n space is the set of all n vectors, so that set of all n tuples of numbers. So it is denoted by Rn, as you know from the calculus course. The two vectors are pairs of numbers, so that each two vector encode one point in the coordinate planes. We can identify R2 with the coordinate plane. The three vectors are just usual vectors in the three-dimensional space, so you can imagine them as some arrows, as physical objects. Now, vectors for matrices. A matrix is a rectangular array of numbers, namely an m by n matrix is an array with m rows and n columns, so that it's an array, a rectangular, with m by n cells. Each cell contains single number. The number which lies in the ith row and jth column is denoted by I sub j. So the first coordinate I, the second coordinate j, and all coordinates took values from 1 to the corresponding sizes, to the number of rows and to the number of columns. The notation, look at the top, I sub j with parentheses, and the limits for the I and for the j are on the top. So the first index I denotes the number, the row number, and the second index j denotes the column number, not vice versa. Examples. For example, look at this formula: I plus j and parentheses, and then, very important to note that I is the first index, so that I is a row index, and j is the second one, so that j is the column index. You see that the matrix has two rows, because I has the limits I to 2, and j has limits 1 to 3, so that the matrix has 3 columns. And the elements which lie on the ith row and jth column is calculated by the formula inside the parentheses I plus j, so that we get the matrix of this form: 2 by 3 matrix consisting of these numbers. Another example: any number is a 1 by 1 number, 1 by 1 matrix. The third example: suppose that matrix B is given by the following formula. You see that, again, this formula gives us a way to calculate each element of the matrix. If you like programming, you can translate this formula to the function that calculates the elements on the ith and jth cell. So that this matrix consists of single row, 4 columns. Each element of this matrix is calculated by the formula g squared. Now, let us consider some special matrices. The row vector is a matrix of 1 by n. The column vector is a matrix n by 1. So each vector n vector can be represented by two matrices, the row vector and column vector. We will identify the n vectors with the column vectors, so that the Rn for us is the space of the column vectors. It is maybe look like something that doesn't important, but later we'll see that there are some points there the row vectors and column vectors are not equivalent to each other. Analogously, the set of all m by n matrices is denoted by this R up m by n. So similar to Rn, the set of n vectors. So matrices are two-dimensional. There are two dimensions, and another one special matrix is the null or zero matrix, which consists of zeros. Each cell is equal to 0. So for each size m by n, we have one null matrix, which is sometimes denoted by bold 0. So very special matrix is the null matrix. Now let us consider some basic operations which can be applied to matrices. Some of them are arithmetic operations, and some of them are special for matrices, and which can't be applied to number, or at least if you apply them to numbers, you doesn't have any new. Now let A be an m by n matrix as before. Remember that this notation means that the first element is A11, the second one is A12, etc. up to m rows and n columns. So the size of A, the size is a kind of operation. It to each matrix it associates the pair of its dimensions, so that the first number is the number of rows, m, and the second number is the number of columns, n. So the size is a pair, m, n. Sometimes we can put m times n. Now, another operation is cutting one row from the matrix. Extracting one row, the ith row is denoted sometimes by a sub I, if the matrix itself is denoted by A. So the ith row is the row vector. Analogously, the J column of A is the column vector, consisting of all elements of this column, so that the row has the length n and the column has height m. Now, one important operation is transposition. The transpose of the matrix, if you have, for example, some matrix, you can just transpose it by this way. So you get from m by n matrix a matrix of the size n by m. The rows and columns are interchanged in the transpose matrix, so it is given by the following formula. The first index in the transpose matrix is J, the second index is I, so that if the original matrix had m rows and n columns, then the transpose will have m columns and n rows. For example, the row vector after transposition gives the column vector, and the column vector gives the row vector. So the two kinds of vector are transposed to each other. Another example. Recall that we have considered the matrix given by this formula. This is just a matrix, 2 by 3 matrix, 2, 3, 4, 3, 4, 5. Now we have the transpose, which is given by very similar formula, but J and I are interchanged. Then we get the following matrix: from the long matrix we get high matrix. From 2 by 3 we get a matrix of 3 by 2 with the rearranged same elements. So the first column was 2, 3, so then the first row of the transpose matrix will be 2, 3, etc. Each column became now a row, and vice versa.